All right, today we're going to look at the analysis of MOS amplifiers. And it's important to note that these are similar to BJT amplifiers in terms of how the analysis is done. First, we're going to find a DC solution. Next, we're going to draw the small signal circuit. And in doing so, we're going to short any AC voltage source and short any DC voltage source and open any DC current source. And finally, if we have any capacitors in our circuit that are large, we're going to short all those large capacitors. Okay, for the circuit that we're looking at here, these are our large capacitors. And we're going to go ahead and try and instantly draw the small signal circuit. So here we can see R1 and R2 are going to be in parallel with the input. We have our gate to source voltage. We have our dependent current source, GM times VGS, feeding into our drain. We have the small signal output resistance of the MOS transistor. We have the drain resistance to ground. And then finally, at the source, we have a source resistance. This is going to be in parallel with that load resistance due to shorting the capacitor out. And finally, we're going to take our output voltage off of that node. So with this model drawn, we can go and start doing some analysis. So let's go to the next page. All right, so here we've redrawn the small signal model on this page, and we're now going to do the analysis of the circuit. In order to proceed, what we're going to do is do KCL on every unknown node. We're going to note in this case that the gate voltage VG is simply equal to VI, since the voltage source VI is tied directly to the gate. And we're also going to note that the source voltage Vs is equal to Vout. All right, so to do the analysis, we just need to write KCL expressions at every node. So we're going to start at the drain node. VD over RD plus VDS over RO plus GM VGS is equal to 0 will be our first equation. We can simplify this a little bit. Here we've simplified this and solved for VD by making the substitutions that we've noted above. VG is equal to VI and VS is equal to VO. We'll next write an equation at the source node. This is equation 3, and we can simplify this and solve for VD as well. All right, now we have two expressions, equations 2 and 4, that are in terms of VD. So if we equate those two, and solve for V out over V in, we'll have our voltage gain. Now, this involves a bit of algebraic manipulation, but I'm going to write down the expression for you. Right, so we have an expression for the voltage gain. And we're going to note that most often the output resistance of the transistor is going to be much bigger than the external drain resistance, RD. And if that's the case, we can simplify the expression a bit. Now we note here that the term that I'm circling in red, we're going to label as big GM. And the term I'm circling in gray, I'm going to label as big RT. Now we'll talk about what this means in the next video.